In section 3.2, we're going to be looking at the derivative as a function. We've already looked at this a little bit in section 3.1, but in 3.1 we calculated the derivative at a particular point. We are always looking for f prime at 2, the function's derivative evaluated at 2. Now what we're going to do is to come up with an entire function that represents the derivative. So there's a little bit of a difference between these. In order to find the derivative as a function, the first way we're going to look at this is by using the limit definition of the derivative. So we want to make sure we memorize this limit definition of the derivative. Right here, the limit definition of the derivative. Now this looks familiar. This is f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. This is the same formula that we used in section 3.1. The difference being here is we're going to be looking at this in terms of the entire function instead of at a particular point. You'll definitely want to have this memorized for tests and quizzes. We're going to use it so often though that I think memorizing will come pretty easily to you. For our first example, let's go ahead and find the derivative of the function f of x equals x squared plus 9x using the limit definition of the derivative. Now remember, on a test or a quiz, those of you who know the shortcut rules, and everyone else will learn the shortcut rules pretty shortly as well. If it asks you to find the derivative using the limit definition, this is the process that you need to follow. First of all, the formula that we want to use is the limit definition of the derivative that we used right up here. So it's always a good idea to copy down the formula. Then what we're going to do is we're going to plug in these values into the formula. Make sure you don't drop your limit notation. F of x plus h means everywhere we see an x in my original function, I plug in an x plus h. So here's x plus h quantity squared plus 9 times the quantity x plus h. That's f of x plus h from up here. This says to subtract off the original function, so here we subtract off the original function. The things to be careful about here are that we have the parentheses in place, because if we don't, the negative won't distribute, I won't get things to cancel, etc. Next we'll want to expand the x plus h quantity squared. That's going to be FOILing x plus h times x plus h, first outside, insides, and last. That will give us this piece right here. Distribute the 9 through here, and then distribute the negative through here. And of course we get quite a few things to cancel here. The x squareds cancel, the 9x's cancel, and this is all good news because we want to get everything left in the numerator have an h involved. The reason we want the h involved is so I can cancel the h into the denominator into the numerator. But before I can do that canceling, of course we need to go ahead and take the limit. The limit here is 0 over 0, which is indeterminate, which means I need to do more work. So we should always show this at some point. Next I'll factor out an h. Remember, you can only cancel factors. Factoring out the h, I'm left with h plus 2x plus 9. And again, the h's cancel. So now for my limit, I'm just left with the limit as h approaches 0. H is going towards 0, so I'm just left with 2x plus 9. So this is basically the derivative as a function. This means that if I have a function x squared plus 9x, the derivative is 2x plus 9. Now if I want to know that derivative at a particular point, I just plug in that point. So you could find equations of the tangent lines, you just needed a particular point. So here, let's suppose that I wanted to figure out what f prime of 2 is. That would be 2 times 2 plus 9. 2 times 2 is 4. 4 plus 9 is 13. So that's pretty simple. Instead of having to go through that entire process that we did in section 3.1, this is a little bit easier. If I wanted to know what f prime at negative 4 was, I'd plug it into my derivative again up here. 2 times negative 4 plus 9. That would be negative 8 plus 9 is 1. So again, this is a lot easier to do because I can just go ahead and plug in a point and evaluate it instead of having to go through that whole process again that I did in section 3.1 for both of these points. Now remember, this would be the slope of the tangent line at 2 of this particular graph. This would be the slope of the tangent line at negative 4 of this particular graph. Let's go ahead and look at another example. In this example, we're going to be finding the derivative of the function f of x equals 1 over x. Now we want to find the derivative as a function. We don't want to find the derivative evaluated at a particular point. So to start with, I want to make sure that we are using the limit definition. Now because I'm using the limit definition, we don't know our shortcut rules yet. It's always a good idea to go ahead and write down the limit definition, and that's what we have here. And again, it's a good idea to start every problem with that. It's not required, but it's always a good idea to get you off on the right path. So here's our limit definition of the derivative. Then what we do is we plug into our original function. F of x plus h means everywhere in my original function that I see an x, I'm going to plug in an x plus h. And this right here is f of x plus h. Minus my original function, minus 1 over x, because that's my original function, all over h. Now something that I need to do here is to go ahead and take the limit as h approaches 0. As h approaches 0, this is equal to 0 over 0, which is indeterminate. And of course indeterminate means to do more work. And the more work that we're going to do here is to find a common denominator, get rid of layered fractions, and hopefully do something with this h in the denominator. Something will cancel with that. So finding my common denominator up here, it would be x times the quantity x plus h. So I'd multiply top and bottom here by x, top and bottom here by x plus h. Whatever you do to the bottom, you have to do to the top. Okay, so in so doing, I have the x minus the quantity x plus h. Now remember, if I don't have parentheses here, the negative sign won't distribute, and if the negative sign won't distribute, things won't cancel as they should. So the x's cancel, and I'm left with a negative h over xh times the x plus h. Let's back up real quick right here. What happened with this h? Well, this is actually h over 1. But when you divide by a fraction, you multiply by the reciprocal, and I flip it and it becomes 1 over h. And so this h is the same one that's in the denominator right here. That's where that h came from. So rewriting here just a little bit, and again doing some canceling, let's see what we have. And of course we never drop our limit notation. So here we have f prime of x equals the limit as h approaches 0 of negative h over xh times x plus h. Now this h in the denominator is a factor, and it will cancel with the h that's in the numerator, but I need to remember that I actually am left with a negative 1. Okay, and again, it's important to never drop your limit notation until you actually take that limit, and I'm not dropping my derivative notation either, because I want to make sure I can distinguish this between the original function and the derivative. So again, I'm left with negative 1 over x times x plus h. Now as the limit h goes towards 0, this piece goes towards 0, and I'm left with a negative 1 over x squared. So let's see what this looks like. If our original function was f of x equals 1 over x, then what I have figured out then, f prime of x is equal to negative 1 over x squared. So my derivative is negative 1 over x squared. This is the slope of the tangent line anywhere along the graph, not just at a particular point, but anywhere on the graph of f of x equals 1 over x. Now, of course, I have a problem when x equals 0 because the denominator is undefined, but we'll worry about that a little bit later. Now, from here you can find equations of tangent lines, and all you need is a value of x to evaluate these. Let's go ahead and look at some other notations for derivatives. The three derivative notations that you see here are some of the most commonly used one. The f prime of x is what we're already familiar with, and the f prime of x and the y prime are both notations that were introduced by Lagrange, and you might have heard Lagrange before when you're talking about Lagrange multipliers. And then we also have this dy dx notation that was introduced by Leibniz. And so again, these are some very common notations to represent the derivative. This one is read f prime of x, this one is read y prime, and this notation means the derivative of y with respect to x, the derivative of the function y with respect to the variable of x. So these are all some common notations.